So yeah, so these are all the problems that we'll be solving using MATLAB. And let's get to the first question. The first question is the topological operation, distance between two pixels. So we know distance between 2 points is root over x1 minus x2 the whole square plus y1 minus y2 the whole square. So we'll be just applying the same thing in MATLAB. So let's just write the program here. So for each and every question, like I have just already solved the questions, so I'll just be running the programs and showing you the output. So here, this is the output for the system, like the difference between two pixels. Uh, 1 second. That's like I'll just be running it now. So the x coordinate of the first pixel, let it be 10, let it be y coordinate of the first pixel, let it be 20. So our first pixel is 10 comma 20 and the second pixel is 30 comma 25. So the difference is 20.615. So this is the geometrical distance between these two pixels. So that does it for the question number 1. So the next thing that we'll be doing is point operations, image negatives, power law transformations. Okay, so image negatives. This is it, image negatives. Yeah. So the first line I am read is about reading the image from my desktop, and this I am sure is like I'm just displaying what image that I have read, and I've just given this a title. So this L here represents the maximum value of each pixel. So here this maximum value is 256, 2 power 8, which is 256. Uh, but for a binary image it would be 1, and for another for a different bit of image it would be like the 2 power whatever the bit number of bits that you're allocating for each and every pixel. And the negative is nothing but the inverse, like not inverse but like how the let's say if no how much, like how far it is from 0, the same thing how it is how far it is from like the highest value. Let's say if your value is like 10, so 10 is like 10 distance of 10 from 0, so this would be implied as like distance of 10 from 255. So that's exactly what I have done here. L minus 1 is 255. L minus 1 is 255, and this I'm just separating the distance from origin, like from 0, and I'm just displaying that. So you can see this is a negative image and this is the original image. Yep. So you can see the dark areas are like much more weighted because they are like from more far. So the next question would be power law transforms. So power law transform just applies the formula for a power law transform is S. S would be the output. Output intensity is equal to C is the input intensity. R and Y, R and gamma are constants. So let's say if the gamma value is greater than 1 implies this kind of curve, which would say the intensity levels are clustered when for lower pixels, like for lower intensities, and in higher intensities they are spread out. So like for lower intensity the contrast is very less, and for higher intensity the contrast is more, and it is the exact opposite for gamma values less than 1. So here I implemented that exact same thing. So this is my gamma array. So this array consists of various different gamma values. So for each and every gamma value, I'll be plotting it in the sense I'll be displaying the image like after each and every gamma, like for each and every gamma like for each and every power law transformation using these gamma values. So let's run this. So I'd be getting 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'd be getting 9 outputs. Yeah. Uh, So as you can see, I've got 9 outputs, and and each of those gamma values, for each of those gamma values. Mm. So next question is piecewise linear transformation, gray level slicing and contrast stretching. Uh, Gray level slicing, yeah. This is the program for gray level slicing. So uh, so for gray level slicing, the main thing to notice here is our input image, this dynode or JPG is a color image, and gray level slicing can be only applied to a grayscale image. So what I'm doing is first converting this input image to a grayscale image using this RBG to gray inbuilt function. And like I want to store the output image in another, like I want to store the output image. This n comma n is the like this n comma n is nothing but the size of like it just stores all the values of b, and I'm just looping through every single pixel in that in this like gray scale image, and looping through every single pixel. And what I'm doing is I'm checking if this value, the intensity value of the pixel is greater than 150, and if it is greater than 150, then I'd be storing 1. This 255 in the sense it is like by 255 in the sense it is white. I had to store like white if it is greater than 150, and if it is less than 150, I'll be storing 0, which is black. Which is obviously black. So the output image is a gray image, but it just has only two color bands, 255 and 0. Uh, Let me just run it. So you can see, even though this is a grayscale image, I'm just having only two bands, 0 and 255. This all these white areas marked 255, and all these dark areas marked 0. And you can also like just change if you want some other, like if you want to do it for some other scaling, and just change these conditions. That's it. Just change these conditions and change the intensity values that you are given. So the next question is contrast enhancement. Yeah. So for the contrast stretching or the contrast enhancement, you can just do a normal histogram equalization, and that's a very easy inbuilt function usage. Histogram equalization of the histogram equalization of the image. This does it. This inbuilt function does it for you. I'll just run and show you the output. Exact. Yeah. As you can see, this image has much more contrast than the original image. So that is contrast enhancement. Yeah. Just clear this memory space. So let's go to the next question. Next question is neighborhood operations. Okay. And average, first one is average filters. So for these filters and for applying a filter to an image, there are like actually two ways of doing it. One is to manually do it, like just looping through every single pixel in your image and applying the filter, or like there is then also another method, like using the IM filter. Uh, IM filter has two input parameters. One is the like what image you want to do it, and H is what filter you want to use. So the filter I'm using is the average filter, which is like 3 cross 3 matrix filled with 1 by 9. So that's what I've written. This is a 3 cross 3 matrix filled with 9 divided by filled with 1 divided by 9. So I'll just run and show you the output. As you can see, the input is like blurred, very blurred. So if you want it to be, if you want to blur it even much more, let's say 4 comma 4, this would like blur it a lot. 16, the run section. Yeah. As you can see, this is like much more blurry than the previous image. Yeah. So like, the H value you can see is like 1 by 16. Each and every pixel here is 1 by 16. Like each and every value of the matrix is 1 by 16. So that is it for average filters. So the next one is minimum neighbor. So this thing cannot be done using a filter, because our filter doesn't know which element is like which value is minimum. So what we have to do is like we have to manually look through every single pixel, find its minimum values, like find its neighbor values, and then choose the minimum value. So that would be a very tough task. Like that would be writing a lot of that would be writing a lot of code, but manual code. But that's like also a much more simpler image, like much more simpler way of doing this. For a binary image, so we know for sure that for a binary image, the minimum value is 0, and so one property of 0 is anything multiplied with 0 is 0. So what we'll be doing is, let me just show you the code, and like then I'll explain what I'm doing. Yeah, so it is. Mm, mm. Okay, I've used actually a different image for this. So one important thing to note here is, uh, okay, let me just do like one important thing to note here is this is only applicable for a binary image. For what I have done is I have just created a filter which is filled of zeros. This F1 here is full of zeros with exact one value, and F2 is the same as F1, but like the one value is in a different position. So I've created 9 filters like this. So 9 filters will be like of each and every for each and every position here. And so when I apply this 9 filters to an image, I can apply this each and every one of these filters to an image, and I'll be getting 9 images, right? So I can apply filter one to my query image or the input image, and I'll get one input, and I can apply the same thing. Filter one. I can apply the same filter to my filter F2 to my input image, and I'll be getting image 2. And what I have to do is multiply all these images just bit and. So if any one of those values is 0, the final value would be 0, and I'll be getting the least value. So the final output would be Z. Yeah. Let me just run this and show you. Okay, that's what I've done. As you can see, this is a perfect. Actually, this image was a perfect chessboard. Now, as you can see, the values are like towards the edges. The values are just fusing together. Now, let me just show you what happens if I just change it to OR. OR in the sense, so OR, what OR does is it gives you the maximum value. If each and every if any one of these values were 1, then the final output value would also be 1. So so your reasonable guess would be the input, like the towards the edges you'd see more white, because white is represented through 1. Okay, yeah, that's the same, like that's the result we have got here. As you can see, the edges are represented in white because I've used OR. On OR takes the maximum value, and maximum here represents white. So let's go to the next question. Yeah, let's go to the next question. Use of average name functions. Okay, operations on set of images. So one thing here to note is arithmetic operation can be done on any image, and logical operators can only be done on binary images, because like these are XOR and not a binary operations, and they have to be done only on binary images. And so let's do AND operations, like addition operation. Hmm, yeah, here it is. Yeah. So X and Y are my two images. Like what I'm actually like, I'm not using two different images. I'm using the same images. Okay. So Z first. I'm just first showing you my. Okay. Yeah. This will do. This will do. Yep. This will work now. So the addition operation like adds both of my images values, adds the values of each and every intensity of each and every pixel. As you can see, the sky was near white. So what happens when I had two huge values is like it would be like let's say the first value was 1 150. When I add 150 plus 150, it would be 300, and like when it's 300 it would be recasted to 255, which represents white. That's what we have gotten. Like division operator, like because I've used the same image, so everything would be 1, so all the values would become 1. 1 is very close to 0, so that's why we're seeing black. Okay. So that is it for addition and division. So next thing would be the logical operators, and or. So this is it. Hmm. And all. So these are like, I'm just using the same two images again, and I'm just first changing this into a grayscale image, and then I'm changing it to a binary image using this I am binarize function. This changes a grayscale image into a binary image, and z is like I'm taking the complement of the binary image, so 1 will be converted to 0 and 0 will be converted to a 1. And next is a bit XOR operation. So let me just say, like I'll let you guess the output for bit XOR, because I'm using the same image. XOR is like when the input signals are different, the output is 1. So because I'm using the same image, all the input will be each same, so always the output would be 0, and what I'd be getting here is a complete black image. And let's say see if that's true. And yeah, not I think I've just renamed it wrong. Let me just one sec. This should be XOR. Okay, XOR. As you can see, the XOR is completely black because I just used the same image, and when I use the same image, all the values would be same, and so that's exactly, and that's why we're just getting this like complete black screen. So if you want, you can just try this for a different image. Let's just go to our next. Let's go to our next question. So our next question here is just one sec. Remove these things. Uh, so our next question is geometrical operation, rotation and affine transformation. Yeah. So an affine transformation is uh, okay. The basic idea of an affine transformation is a set of parallel lines remain parallel even after the affine transformation. That is like the number of, like, let's say a set of points lie on the same line. Even after like the transformation, all those points should lie on the same on a same line, but those two lines can have different slopes. Meaning, uh, by the slope of the lines can be different, but all those points should, like, if n points lie on one line, all those n points should lie on a different line. Like after transformation, all those n points should lie on a different line. That's it. So we can do any of these transformation, a translation transformation, or a scale, or a shear, or a rotation. So what I have done here is, let me just check. Yeah, I have done a translation here. Um, as you can see, the translation. This is my translation filter. Like the matrix that I'm using for translation. So like the diagonal elements are filled with 1, and these two contains the displacement along x and y. So that's exactly what I have represent here in H. So displacement is 4 comma 4. So let's just see the final output of this image. So as you can see, everything has been displaced by 4 units in x-axis and 4 units in the y-axis. So, and for rotation, and for the second question is about rotation. So for the first question was about rotation. So for rotation, what we can, like, that's actually an inbuilt function to rotate an image. So I just have to specify at what angle that I have to rotate this image with, and that will do it for me. So let me just run this section and show you. So I can see the image is rotated by 90 degrees because the input parameters are given 90. So let's go to the next question. Next question is statistical operation, mean, variance, downsampling. Okay, nice. So we want the mean and variance of an image. So my B1 is a binary image and my X is a color image. Okay. So as you can see, this has three dimensions. So it is a color image, and this also has three dimensions, but this is like into one. 512 into 703 into 1. So that is a black, a binary image. Yeah, this one is a color image. So what I have to do is find the mean of, there's an inbuilt function called mean, which is automatically calculates you the mean of whatever you want. So let's just type mean. Okay, yeah. So now I've gotten the mean of all of these function mean of. Okay, so what happened is like the mean value, the mean calculates the mean of all and mean of every column. So what we want is the mean of all columns. So what we'd have to write here is just put another mean over here, and you can, this should work properly now. Yeah. So since we know this is a binary image, so the all values have to be between 0 and 1. The mean value should also be between those, and that's what we've gotten. That's what we've got here. So the next would be to apply variance. I have got the variance of this B image, B1 image. So let me just clear all of this. Yeah. Let's go to the next question. Next, then the final question is image interpolation downsampling. So what is downsampling? Downsampling is like reducing the number of pixels in our image. So reducing the number of pixels would automatically result in loss of clarity. So that's what you're going to do. Like for downsampling an image, we have another inbuilt function which does this for us. So that would be IM resize. Yeah. So you can read one image here, and you can resize this image to any other image of whatever pixels you want. So IM resize automatically does this for you. Let's say what we want is 100, 150. Okay, I'm just getting a chest. Let me just change this to dino because it will be more visible. The effect will be more visible with this image. So this is my original image, and this is my resize image. So as you can see, there's a lot of loss of clarity because the number of pixels here are very low. So I've just used 100 and 150 pixels where I don't know how many, but I've certainly used more pixels to represent this image. Okay, so that's it. That's the final question, and I have covered all of these questions in this video. Thank you.